Okay, so last time we were looking at these some amazingly nice theorems, okay, and we'll carry on looking those nice amazing theorems. Look, I'm drawing not straight line, which also means that my brain is not straight. Okay, so the theorem which we first wrote, let G be a multigraph, okay, then G has K edge disjoint spanning trees if and only if for all partition of vertex sets for if and only for all partition of vertex sets we have at least k times L minus 1 crossing edges, right? So this was our packing theorem. Okay, and what was our covering theorem? The covering theorem was a multigraph G can be covered with at most k edges, k spanning trees, okay, at most k spanning trees if and only if for all U subset of Vg number of edges okay how much it was? Is that fine? I think somehow my feeling is okay, so that's fine. Here shouldn't we use the fact that graph should be connected? Because I mean, look at, start with a forest, no? That also satisfies this condition, right?
But then k will be not equal, k will be 0. There is no spanning. So k will be 0, and so for every forest you can do, every tree of forest.
What is that? What tree? No, but like what are you covering with? What's an object? Yeah, so either we change it to a spanning forest, or let's assume that the multigraph G is connected. That's it. Because then what happens, if you give me a forest, I can make it a tree by adding edges, right? You can convert any forest into a tree, right? No?
No, if we take U as a subset of Vg and we take some vertices from one tree, some vertices from other tree, then this will this be this bound rule?
This has nothing to do with this. For every subset U, this many edges should be there. Yeah, of course it will be there. Look, you say that if you take a forest, this bound will hold.
No.
What is this bound tells you? This bound is tell you that number of edges here is very small. So put k equal to, and it just tells you it's a forest. That's precisely what it tells you. So if you take an induced subgraph of a forest, you will still get a forest.
No, I'm saying, okay, if you are taking a forest, then for you, I'll choose one vertex.
Yeah, I'm telling you here.
Yes.
Yeah, so it doesn't matter, no? Look at the edges induced on that. Okay. So I think how the way it is phrased in the book is slightly different, and that's, I think now I understand the way it has, the way they have phrased is that, okay, your subgraph may not be the spanning tree may not be the subgraph of the graph. Okay, so that is how it is phrased. So it can come from anywhere. It's just that I require that. Okay, so think of this, that you can take a complete graph on this vertices, and from there you are picking up things. Okay, but for without, just to not have a confusion, let's assume this graph is connected. Okay, otherwise we might end up into, like, there will be unnecessary coordinate cases. Okay, and what is the theorem that we wanted? What is the theorem that we would like to prove? So the theorem which we wanted to prove was the following. So what did we say? That you are given a multigraph G, an integer k. Okay. Okay. So what does this theorem say? For every multigraph G and k in natural number, there exists a partition P of Vg. Okay, there is a partition P of Vg such that what happens? Such that every graph induced on U with U in P has k edge disjoint spanning tree. Okay, and if you contract the edges of G and G by A, graph obtained by contracting edges of edges of each partition, that is what it is, G, right? And G slash P, what is the property? And G slash P and edges of G slash P can be covered with at most k trees, spanning trees. Okay, that's what it is. Okay, fine. Okay, if I use this more, I will get confused more. Okay, so this is what it is. So basically, it says that you are given a graph G and a natural number k. I can come up with a partition of vertex set, okay, into, say, this is U1, U2, U3, dot dot dot, I don't know what it is, right, UL, right. So these are my partition of my vertexes, and what is the property that if you look at a graph induced on this, each of these guys, what is the property of this graph? That you can cover them, there are like some k edge disjoint spanning trees in each of them. And if you look at the crossing edges, okay, basically it says that, forget it, look at the crossing edges, I can cover all the crossing edges by at most k spanning trees. That's all that it says. That look at the crossing edges. So the way to interpret this is crossing edges can be covered by k trees, k spanning trees. They need not be disjoint or something, right? So I can find k spanning trees in my graph which can actually cover these guys, cover each of the crossing edge. This is what the second condition tells us. And what the first condition tells us? The first condition tells us if I look into each of this graph induced on these components, right, then they have k edge disjoint spanning tree. So what are these? They are like sources of denseness, right? And what is, if I look across, this is a source of sparseness, right? So sparseness is useful for this, denseness is useful for this, right? So it's a basically a structural theorem which tells us that given a graph G and integer k, we can partition our graph into some form of k dense things and across things are sparse, right? So you can think of this as some dense sparse partition. Okay. So this is why this is very useful, because I mean I personally think that this should have much more utility than what we are able to see here. Okay. So now I want to, so this is why just this theorem implies both these theorems. Before for each of these theorems you needed a different proof, right? So now in some sense it's a unified proof which also gives you a very nice structure theorem for the graph, because it says nothing, right? What it says, if you give me graph G and an integer k, then I can partition my vertex set into something such that each of them are k. Look at what is the graph induced on this. I can also say they are k edge connected, right? Because if they have k edge disjoint spanning trees, it also implies they are k edge connected. Because look at any two vertex here, they have paths in each of the spanning trees, right? And they are edge disjoint spanning tree. So between these two vertices, how many paths are you able to support? You are able to support k edge disjoint paths, one in each tree, right? Which also implies that each of them are k edge connected. So they are like very, and what is the property of this here? That they cannot be k edge connected, or they are at like, if I can disconnect some of these things with much fewer edges, right? Because across edges are much less. Okay. So for example, if you had some click kind of object on small number of vertices, where will they lie? They will be somehow captured in these UIs, because if they go across or something, you have far too many edges that you can't even support that. Okay, fine. Okay, right? So because look at the counter examples that we were trying to make, right? For these theorems, this statement is true about any graph and any integer k, right? Right. So for some right number k, something interesting will happen. Then what will happen? Those clicks or something will be captured in one of these guys. Okay. Suppose graph has k edge disjoint spanning trees. What will this partition look like? Suppose graph has k edge disjoint spanning trees. What could be one potential partition? Huh? That's itself, right? Because it never says that this L has to be greater than or equal to 2 or something. No, all it says that I can partition into some L pieces. L could be any number between 1 or something more. Okay. So now let's try to prove how this theorem implies packing theorem and how does it imply covering theorem. Okay. So let's see why does it implies packing theorem. So what will I apply? I will, given a graph G, so we already have seen forward direction for both of them, right? That if you have this, then this property holds, right? What is not obvious to us was how does the converse hold. So let's try to prove the converse. Okay. So now I say, okay, fine, given a graph G and integer k, let's apply this theorem here. So what are we going to get? We are going to get some u1, u2 dot 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 some un, right? We are going to get. Now, what we know about each of these components, that they have k edge disjoint spanning trees. Okay, so let's name them. I'm going to call them T11, T12, T1k. Like for the first partition, there are k edge disjoint spanning tree on this. T21, T22 dot 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 Tkn, T, so on and so forth. So for the L, they will have T1L dot dot dot, no, TL1, Tk. Okay. So this is how the spanning trees are in each of them. Okay. Now, but look at this partition and look ourselves, how many crossing edges are there? Look, because of the converse property, you come up with any partition, it has to support some number of edges. So I applied my graph, I asked for this partition, so it gave me some partition. Now I am asking myself, how many edges are going across in this partition? Okay, so how many edges are going across in this partition according to our statement? So this is at least how many times? K times L minus 1 are crossing edges. Okay. What does my theorem tells me? That it tells me that look, you also at least need, okay, so now if I contract each of these vertices, each of these component, right, into singletons, preserving all multiple edges, whatever going across, right? What is a, how many, like what is a number of edges a spanning tree on this L vertices can contain? L minus 1, right? Now, how many edges do I have? Okay, so you have k into L minus 1 edges. And now, what does this theorem tells us? That we could cover all these crossing edges with how many spanning trees? K spanning trees. Okay, let that spanning tree be W1, Wk be the spanning tree. Now you ask yourself, can W1, can any two spanning tree share an edge? Because if they share an edge, how many total, in total they can cover edges? At most k L minus 1 minus 1. But you have at least, how many edges you have? Is at least k into L minus 1. How many edges these guys can support? Is at most k times L minus 1, which implies that this W1 to Wk are edge disjoint. Okay. So now what we have been able to achieve? W1, W2, Wk are edge disjoint. Okay. Now how I am going to make k edge disjoint spanning tree from my old graph is very simple. Okay. You take T11, T21, okay, TL1 and W1, okay, that's a spanning tree. Do you see why it's a spanning tree? What happened? You start with W1, that's a spanning tree where these are fat vertices, right? For each of those fat vertices, I have replaced it with a one spanning tree from this, right? So similarly, this is one spanning tree, and similarly you can get T so T1k, T2k, TLk and Wk is another spanning tree. So this is the way you can construct k edge disjoint spanning trees, right? So internally they are disjoint, externally also they are disjoint, right? So this gives us a proof that if you did satisfy this requirement, I can construct k edge disjoint spanning trees. Any question? Okay. So now we will try to prove this theorem starting from this theorem. Okay. Okay. So now what we have to prove? Okay. This is also will be very simple. Please.
Why is the number of edges, crossing edges greater than equal to k times n minus 1?
Because we are assuming this would say that every partition of my vertex set, right, every partition of my vertex set had at least this crossing edges. So because we are assuming this condition, so I said okay, let's apply that condition on this particular partition, and that's it.
Could you extend this last spanning tree one this T1
What did I do? So across I have k edge disjoint spanning trees. Okay, I pick up one spanning tree. I pick up one spanning tree each from each of them, and I'm saying that's a spanning tree. Right? For the second, I took the second copy, like second spanning tree from it. For the third, I picked up the third spanning tree from this. For the fourth, and internally each of these are edge disjoint spanning tree, edge disjoint. So what? So at least as in they are part, like they each, this contains a different set of edges compared to this and compared to this. Now why are they forming a spanning tree? That is because you look at the clubbed graph. Look at the W1 is a spanning tree here. Now replace this big vertex with the T1 is spanning tree, because that is still, because someone will be this edge is connected to some vertex here, no? That's it. Okay, it requires, it's not like, I mean, if you want to have a formal proof for that, you have, but it's not something very, like, it's literally like you replace this with, so look at any edge in this W1 spanning tree coming from there. For every vertex, there is a vertex in your spanning tree which is connected to, and that's it. And internally they are connected. Okay. If I go into that much detail, then we will never cover these things. Okay, fine. So this is what it is happening. Okay. Now I want to prove this. Okay. So I'm going to rub this because that's my workspace. Okay. Or maybe let me. Okay, I don't know. It's more or less similar kind of things only. I shouldn't be using black. It's like, it really makes it. Yeah, I shouldn't use black. It's like really dark stuff board. Okay, so now what I do is the following. Okay, so now we have to prove that this direction, right? Okay, so as always, I will G and K, I'm going to apply this theorem, get my partitions. Okay. Okay. Now let's ask ourselves. Now let's go into each of them. Okay. What is our objective? Let's try to understand it. What is our objective? Our objective is to cover all the edges with some k edge disjoint by at most k spanning trees, right? So look at the crossing edges, right? Look at the crossing edges. By definition, they are covered by k spanning trees. Look at this theorem. All the crossing edges can be covered with k spanning trees. That's what it says, right? Okay. So let's keep that row tree. Now let's go back to each of them, each of these guys. Okay. What does theorem tells us? They have k edge disjoint spanning trees. Okay, so let's give them name again. T1 1, T1 k here. Okay.
In the backward direction, we have this partition.
Yeah, we'll get there, no? So this is exactly what I will use to show that it covers.
No, but we assume that this contains k.
That's because of the statement of this theorem.
Oh.
I applied G and took this k and I applied the theorem. So theorem gave me this. Okay. Okay. Now, so how many edges these guys has? How many edges these guys has? k times, right? Because they are edge disjoint spanning tree. And how many edges are allowed to be here? Every induced graph U contains how many edges? You look very confused, Pratik.
Thinking about previous one, right? But in the previous one, there at most k trees, right? Would be a
No. No, we k edge disjoint spanning tree. Where can be covered with crossing edges can be covered with at most k spanning trees, but it had far too many edges that you need all the k edge disjoint spanning trees. You get my point? You had, look how many crossing edges we had. Okay, so how did we do? Look, so we said G contracted P can be covered with at most k spanning trees, at most k. So now you contract each of these guys. How many vertices you have? How many vertices? If I contract this L parts, I have L vertex, right? If I have L vertex, you ask how many edges a spanning tree can contain? L minus 1. Now, if I give you k, if all your edges can be covered with at most k spanning tree, how many crossing edges can you have? At most k times L minus 1. But you told me that you have at least k into L minus 1 edges, right? Which implies that the spanning tree that you have used to cover all these edges, they better be edge disjoint, otherwise you cannot support that many edges. So it's a cardinality which forces these edge disjoint spanning trees to be disjoint, okay, which is going to force now something else. So now I know that each part has k edge disjoint spanning tree. So how many edges this is supporting? K times cardinality of U minus 1. How many edges does this graph has? At most this, k times this, right? Now, is it possible that some edge is not part of this spanning trees? I have k edge disjoint spanning tree. They are spanning how many edges? K times cardinality of U minus 1. Okay. Now you told me that in this subgraph, how many edges do I have? At most k times mod U minus 1. So now I say, then I claim to you that the k edge disjoint spanning tree that you have talked about contains an edge, all the edges on this, because if some edge was missing, then the total number of edges this k guys can support is only k times this. That's not possible, right? You are covering that many edges. So, or in other way, if I have a k edge disjoint spanning tree, I am definitely covering these many edges. And how many edges are there anyway? At most these many edges. So you are done. Okay. So now, so in the forward direction we use crossing to say at most to at least, and now we have used an upper bound on edges to say at least to at most. Okay. Once we have this, then we are done, right? Again, I can take my spanning trees or whatever you want to say as follows. Look, when I write W1 to Wk, this is not right. Okay, I should say Wk prime, because it says can be covered with at most k spanning trees, where k prime is less than equal to k, right? That's all that I want to say. Okay, so now what happens is that you pick up each one from again, right? Those guys cover, and for the last guy, I mean, I don't care, right? For the last guy, take last guy, that's a forest, then make that into a spanning tree, right? So what will I do? I will do T11, T1k, W1, okay, and maybe T1 k prime. What is this? Okay, no, this is wrong. No, yeah, T1 k prime. This was wrong. This is TL1. Okay, because the first copy. Okay, so T1 k prime, TL k prime, W k prime. Okay, for remaining there is no Wi, but those are like forest, right? Once you have a forest, if the graph is connected, I can convert this forest into a spanning tree, and hence I am able to cover all this. Okay, So basically what happens that once you have this theorem, you have enough copies of everything that you can just put them together to either match the statement of this theorem or either match the statement of this theorem. Okay. So now I am going to spend all my energy on proving this theorem. Okay, unless people have other questions. Okay. Yeah. So this theorem proof is like Tour de France. So just go on Tour de France. This is not something which I can keep in my head. So okay. So let's set up some notation, and these kind of notation you have seen quite a lot being used, but you will see being used like, okay. So suppose you are given a tree, this is a tree, okay, and I'm going to use the word E is chord of T if like T does not belong to, just like a, okay. And this unique cycle is called fundamental cycle. So look at any tree and you put an edge which is does not belong to tree, it is going to connect to two vertices. Okay. Look at the unique blue path between them and take this red edge, that forms a cycle. These are called fundamental cycle. Okay. Okay. So any edge which is not on the tree are like a chord to the spanning tree. Okay, and let this be an edge on an F be an edge on its fundamental cycle.
What will be a non-fundamental cycle?
What?
Like which kind of cycle will be non-fundamental?
Suppose there are two edges if you make that like, okay. Okay, so are you trying to tell us, okay, how many cycles a graph can have? Okay, how many fundamental cycles are there given in spanning tree? If I fix a spanning tree, how many cycles are there? At most m minus n minus 1, which is like n square at most, right? So every other cycle that you can conceivably think of, right? Or let's look at any cycle that contains at least two edges from outside is not a fundamental cycle, right? For example, and there could be, I mean, if I delete this, there could be a cycle just here itself, completely outside, like this, right? So this is a fundamental cycle, but I mean, it will not be like this, like, because every edge is going across some vertex. So it's like, but then it's like I go from here, I go to another guy, I go from here. So if I look at this common path, this is a fundamental cycle. If I look at this, but when I look at these, it's not a fundamental cycle. Okay. So basically any cycle that contains, and every cycle that contains exactly one outside this is a fundamental cycle. here is my E, and look at some F on this, okay, F. What will happen? Yeah, delete F, add E. Is it still a spanning tree? Right? F is a tree edge, okay. F is a tree edge belonging on the tree edge belonging on fundamental cycle. Okay, is that fine? Okay, and this you must have seen in when you were trying to do proof for correctness for Kruskal's or Prim, right? This is how, right? That okay, if this is not minimum, then I can replace some. So this is an argument we are going to do today, but okay. So this is like you are going to. This is like T prime obtained by exchanging F for E. So we have exchanged F for E. Okay. Now I am going to define another set of notation. Okay. Okay. And this is slightly. Okay. So it will. So suppose T is a family of spanning tree. Not one. T1 to Tk. Okay. Be a family or spanning tree of G. Family of spanning trees of G. Okay, be a family of spanning tree of G. So they may not be edge disjoint. So, but they are like some K spanning trees of G. So this is like tuple. Think of them as a tuple. Okay. 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 Now we are going to call a sequence E0, E1, En, okay, a sequence of edges as exchange chain for T if the following properties hold, okay. Exchange chain for T started at E0. So it's like an exchange chain. So what will exchange chain will started at E0 if first En, the last guy, does not belong on any T1, T2, Tk. Okay. So I'm going to call that last guy this guy. So this is a sequence of edges. Okay. I'm saying that it's a sequence of edges start exchange chain for T starting at E0 if first En, the last edge, does not belong on any of these spanning trees, and for all I less than n, strictly less than n, there exists J depending on I such that what happens? Such that yeah, once we get the definition right, okay, such that EJ or EI, okay, yeah, such that EI belongs to Tj, okay, EI belongs to Tj, and EI plus 1 is a chord. Okay, let me. This is a very ugly place to write this definition. This is a very important definition. I shouldn't be writing like that. Okay, so let's. Okay, so what I'm saying. Look at T, T1 to Tk, and you have sequence of edges E0 to En. Okay, I'm going to say that. Okay, is a sequence starting at E0, okay, for T if the some conditions are. What is the first condition? En does not belong to any of the trees. Okay, any of these trees, En does not belong. Last edge. Secondly, for all I less than n, there exists a spanning tree j depending on I. Okay, such that what happens? Ei belongs to Tj and Ei plus 1 is a chord. It means Ei plus is not on Ti and Ei is on fundamental cycle with Ei plus 1. Okay, so what is this meaning? So first one is EG condition. Now you give me any edge Ei, I will tell you a spanning tree here. What is the property of this spanning tree? So look at this spanning tree. So this is your Tj. Now what is the property of this? It contains this Ei, okay, but it does not contain the edge Ei plus 1, okay, and but if you add Ei plus 1 to this, okay, if you add, say, this is your Ei plus 1, then look at the fundamental cycle that Ei plus 1 creates. Ei belongs to that fundamental cycle, or in some sense you can think of this that if you add Ei plus 1 to this spanning tree Tj, then you can evict Ei, right? So with respect to spanning tree Tj, you could do exchange for Ei plus 1, right? So basically what is an exchange chain means? Exchange chain means that for every edge, right, every edge on this, there is some tree which this edge belongs to, and the edges which is preceding him can be used as an exchange. Okay, so this is what it means. Okay, but the way it is phrased it will take some time to get used to this definition. Okay, and it is very natural to believe that En does not belongs to T1, because what are we trying to do? In some sense we said let's start with this spanning tree and we will do some more operations on them to eventually get to some set of spanning tree. Okay, now before we prove a property of this exchange chains, okay, so what does this exchange chain tells you is a okay, so let me write a property of nothing. It could be first this, I don't know. So don't, it's very natural to think that oh E0 will be first one, then I will make modification. Don't, because then you are only talking with respect to one spanning tree, right? Now we are talking about, it's like several spanning trees I have kept. Okay, I have kept several spanning trees, right? But look, E0 belongs somewhere, E1 belongs to some spanning tree, E3 belongs, because we have to create several spanning trees. No, we don't have to create just one spanning trees, right? So all the operations that we think of on doing on one spanning tree, now we are trying to mimic that over a like family of spanning trees. Okay, and so these definitions are in that spirit. Okay, you will see where this definition is used crucially, okay, in a minute. Okay, so suppose this is your definition, and let's try to prove this theorem. Okay, we will encounter trouble and then we will go back and prove those lemma as we encountered trouble. Okay, so this definition I will keep for you. Okay, I am not going to give prove the property of this. We will see what property we need from this statement, and we will see if those properties are satisfied or not satisfied. Okay, but only two things which I want you to, okay, given a tree, if a tree edge does not belong to that, that's like a chord, and if look at that edge creates a unique cycle, any tree edge on that cycle are fundamental cycle. Okay. Okay. So now I'm attempting to give a proof for this. Okay. So what I'm going to start with, I'm going to start with a tuple of k trees which maximizes their union. Okay. What I mean by this? So look at this. I'm going to call it. Okay. I'm going to use. Okay. Just because I can't, I'm going to use t like this. Okay. For the tuple. Otherwise, I will be keep using t and t1 to tk. So let's either give me some notation for this, or this something. I don't know. Okay. Pi looks better. Okay. So what is E of pi is basic. Huh?
N is the number of vertices.
N has nothing. No, it's not. Absolutely nothing. It's like En is a sequence. So look, okay, you're right. Maybe I shouldn't be using n, right? But like, okay, let's stick to it, because otherwise I will have to keep track of so many numbers in my head. N is not number of vertices. Let's write it. Not number of vertices. Okay, I'm not very well versed with this proof. Okay, so you have to be on toes. Okay, what I mean that pinpoint inaccuracies, mistakes. Okay, so what is E of pi? So E of pi is basically union of edges of Ti. Right? So you look at the union of this. So what I want to find, I want to find tuple that maximizes what? E of pi. Okay, that maximizes the number of edges that is possible. So if the graph had k edge ratio and spanning tree, what will happen? What will we pick? Huh? Yeah, like if you have to maximize. So if graph had k edge ratio and spanning tree, then what will be T1 to Tk? Will be those, because that is the tuple which will maximize the number of, because how many maximum number of edges this is possible is k times Vg minus 1. Okay, now that I have used this, so how many what is this upper bound? This is size of this is upper bounded by k times Vg minus 1. But if you did have k edge ratio and spanning tree, what will you pick then? You will have to pick all the edge ratio and spanning tree. So I start with this, and I say, look, this has some nice properties. Okay, this itself has all the nice properties. But now, okay, you came up with this, but like there's absolutely does it look like any clue from where we are going to get these partitions? Okay. Okay. So now what the proof defines is a very funky thing. What is D? Set of all edges in G, set of all edges in G that starts
Are these PIs are spanning trees or?
They're spanning trees. Yeah. Maybe let's assume they're connected for all this. Okay, okay, fine. Connected, but I don't think they're required. Okay, we'll see. So set of all edges in G, set of all edges in G that starts an exchange chain for pi. So what is D? Set of all edges of G that starts an exchange chain for this. So now let's pick up an edge which is not in this. Let's pick up an edge which is not in this.
So, in the definition of D, pi is the one with maximum coordinate.
What?
In the definition of D, the pi we use is the one with maximum number of edges.
Yeah.
The same one we use.
Yeah, this is the same pi. So now we have fix this pi, and we are defining everything with respect to this pi, because so I have a definition, right? It's a sequence starting at some property if this holds, right? This property holds. Now look at an edge E that is in EG minus E pi. Does E belongs to D? Is a question. Look at an edge that does not appear on any of these spanning trees. Does it imply that E belongs to D? Yes or no? En does not belong to T1 to Tk.
E has to, if E starts or extends chain, it has to belong to some T1 to Tk, right?
But EI is the starting. We are exchanging with EI plus 1. So EI should be in the tree. So E0 should be in the tree.
So this is E can like be a single sequence, single.
Yes, single sequence where it says last one does not belong to T1 to Tk. That's all it says. Read. This is, X is empty. Doesn't, like this is vacuously true.
Sorry, what is empty?
Rest everything is empty. For all I less than n, which is nothing anymore, right? Because look at the last one, right? Which is my last one? Nothing. All these edges are on the fundamental cycle with some empty edges. Just put them. Yeah, so this is the first magical part. Because they are singleton exchange chains, right? Why they are not singleton exchange chains? Right? Each of them form a singleton exchange chain. Okay? They are singleton exchange chains. And that is true, no?
But it is starting at E0. And
Like, what is the point of, like, there is no problem. Yeah, it is starting at this.
but then it can't end at this, no? Because
Why?
it does not belong.
Why? Look at the definition, no? It's a singleton exchange chain. If I put this E, does it satisfy this requirement, definition? Does not belong to any of them. That's fine. For all I less than n, right? Yeah, what is this? There is nothing else. This is vacuous. Empty edge. What is it? Yeah, there is something. Empty edge. Right? With respect to empty edge, you associate any tree. You put that tree. Okay. So, like, look, the difficulty part is to get used to the definition. This is why I wrote it here. Okay. This is exactly what I said, right? That this is like. Okay. Now, look at this. So now I am going to consider the following graph. Okay, but there are other singleton chains, right? Like, okay. Or if you are not happy with this, I can actually tell. If you are not happy with this, okay, D is all non-trivial plus everything else. Make yourself happy if that makes you happy. I mean, it's up to me how I define this set of D, right? Right. So I said, if you are not happy with singleton chain you are not able to keep in your head, then here is my definition. Whatever you are able to keep in head plus everything which is not on this tree is my D. Okay. Don't add pressure to your head. It won't change much. Like, it's up to me how I define D. It's just a very succinct way of saying something. But if you are not able to keep, okay. So all those set of all that starts an exchange chain of size greater or equal to 2 for pi plus, okay, Eg minus E pi. Is that fine? That's okay, right? If you are not happy with a singleton chains, then all 2 plus and everything which is not in this, and I'm okay. Okay. Now, so whatever you think is appropriate for you, please that. Okay. That is not going to. I don't think that should change the strategy of the proof. Yes.
T1s are not usually is disjoint.
No.
Then can this type of edges
Which way? What kind of edge?
be singleton?
Like outside?
If it doesn't belong to D.
I do not get your point.
Then we can add this E to this TK
Why?
to create a fundamental.
So that's why you cannot add that. No, I'm not.
I'm adding that and removing one edge from fundamental side.
So
It will create a new T1 which doesn't belong to that side.
so I don't, like T1 to TK is some fixed set of trees.
It maximizes the number
Yes. So are you able to increase the number of edges?
using that table.
What type of edges? How? But you are removing something, no?
It is not increasing, it is remaining the same.
No, if we add this edge to the last TI,
Huh?
TK, it will create a fundamental side.
How it creates a fundamental
Now,
cycle.
remove one edge, except that edge from this fundamental side.
So how do you know that you have maximized the number of edges? How do you have increased the number of edges?
That will be E pi plus 1.
How? You also deleted an edge, no? Otherwise, it's not a spanning tree. Okay. Okay. So now let's consider a graph on the vertex set being V, edge set being D. Okay, and look at the connected components of this graph. This is my graph H. What is this? My vertex set remains the same, but what is my edges? This set of edges. Now look at the connected component of this. Components of H. Okay, okay, and those are like U1, U2. This is my partition. What are these? This connected component of this graph is my partition. Okay. Now we have to show that all the properties are satisfied, right? I mean, have to have a patience, but we are getting there. So this is why I say this is a very magical proof, right? So what we have created is we have created this U1 to UL. Now, if I want to say that this is the right partition, what I have to show? Each UI has a k-edge disjoint spanning tree, and every edge across can be covered with at most k spanning trees. Right? I have to prove this. I'm not saying, all I said, given this set of definition, I have created my partition. That's it. Okay. Now we have to go through and prove this. Okay.
Partition can have just one.
Singleton vertex. If that is what your problem.
This partition can just be one, right?
Yeah.
It could be completely connected.
Completely connected. It could be. For example, you apply k equal to 1, right? And graph has two edge disjoint spanning tree. What will be the other part then? It's just going to be 1, no? That is exactly my point. So if, notice the proof, right? If you are applying a graph G with some integer k and the graph has k plus 1 edge disjoint spanning tree, then whatever you do with k, I mean, you might be able to so you could apply this theorem with just k edge disjoint spanning tree, which is independent of that, and you will get everything as just one partition. This is exactly what I said, that most likely if the graph has lots of edge disjoint, more than k edge disjoint spanning tree, this is going to be a trivial partition, the whole vertex set. Right? Okay. Okay, so I will still keep, I'll remove this. Okay, by now we know what we expect from here, but I still need this definition. Okay, because now I have already created what I want. And notice what is the funny part, that if I show that I can cover all the edges going across, right, then I have covered all the, look what I mean. So I will not show to you that how to say this. Okay, you will see. Okay, what I wish to say, that look at all this D, no, right? Here inside each of them I am going to work on these objects, and across I will also be working somehow on these objects, but those objects will be covering everything that we desire. Okay, we'll get there. Okay, so now let's focus on each UI, and let's say why do they support k edge disjoint spanning tree. Okay, so let's, without loss of generality, let's assume that we are going to focus on U1. Okay, and now I'm going to focus on U1, and I'm only going to focus on the edges from D here. Okay, edges from D here. Okay. Okay, so what I'm going to do, look at this. Okay, so what is going to be, okay, so now for j equal to 1 to k, let's say I, what is this, right, Sj okay, so let's say some u, let Sj be the subgraph of Tju, subgraph of T containing edges from D. Okay, so that is what my Sj is, right? Look at this, look at this. Look at the jth tree and look at the edges that it contains from D here, that is going to form Sj. Okay? I am going to show to you that S1, Sk are edge disjoint. From D. What?
Because D is a set of all starting edges. All edges that starts an exchange there. But every first edge of exchange chain
belongs to that.
Does not belong to anything.
Where it says it doesn't belong to?
Oh, last does not.
Last does not belong to. Everyone else belongs to.
First belongs.
Okay. So now this is where we would like to use the fact, some nice property of okay. So what we will show first that this is edge disjoint, and secondly we will show that each of these SIs are connected, okay, and so S1 to Sk are connected, and then we are done. Okay. So first I will show these are disjoint, and then I will say they are connected. Okay. Now there is a lemma which says the following, okay, and this is about the starting point of, look what it says, if E0 starts an exchange chain, okay, starts an exchange chain for pi and lies in two of its trees, okay. What is it? If E0 starts an exchange chain for some sequence pi and lies in two of its trees, then there is a family pi prime, okay, pi prime of k spanning trees. So for pi, exchange chain for pi is like T1, T2, Tk, then there is a family pi prime of k spanning trees, okay. And what is the property of this pi prime is that G such that, what happens, such that edges of pi is properly contained inside edges of pi prime. Is that fine? So what it says that if E0 starts an exchange for some sequence, and if this guy belongs to two different trees, then we can get a family pi prime of spanning tree of G such that this property holds, right? I can get a bigger set of trees, okay. Now this is, suppose now if I prove this lemma independently, then I can apply this to this fact. Why? Because what I am saying, what is S1 to Sk are containing edges from D. So what is the property of these edges? The edges of these properties are that these are set of all that starts an exchange chain for pi, right? Okay. Now anyway those are not going to contain these kind of edges, because these are anyway we have. So this is why I said let's not worry about them. Their role will come later. So even if you have taken non-trivial these things, that would not have mattered for us. But look at what this tells us. If look at these starting exchange chain, if any of them appears in two of them, then what happens? Then I could get another pi prime that contains all these edges and at least one extra. But that will contradict the fact that we have started with set of edges, set of trees which maximizes E pi, right? So if we prove this lemma, this is fine, right? Okay. So I'm just trying to bring down whatever we need and then go back and prove those things, okay? So as less clumsiness as possible, okay? But now we have to prove that S1 to Sk are connected, okay? And then we will where D will come into play later, okay? Okay. 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 I still need this definition, okay? So I don't need this, okay? Let's keep them here, okay? And connected component of H are U1, U2, UL, okay? So just that we have all the information here, okay? I still need D, okay? Now notice, how did we go about containing, how did we get U? How did we get U? Okay, we got U by looking at the connected component of H, right? So definitely edges of D do form a connected object in H. I am not talking about here, okay? So what I mean by this, what I will show to you, that look at UI, okay? Look at any look at any u, okay. Now some edge, and look at the edges of d into d into what do you call, I have to show this, right. So let's say, right, this is what it is, right. This is what, say, some S1 is. Now what I want to say, there could be two things. Either there is an edge between these guys, this edge, look at this D, this component is a connected component in my H graph, right. So I want to say that look at the path, look at, so either look at any edge u prime in D, okay, where u prime is in U. Let's look at these, okay. Now what could happen, either this edge is there, if all the edges of u prime in D, okay, where this, if they all belong to this, then you are done, because this was connected, so you are connected. So your only problem is that some edge which belongs here, that does not belong here, right. That is your problem, that could be, that is your potential problem, okay. So now what I am going to show to you, okay. So I am going to show to you that, okay, let's say some Sj, okay, fine, some Sj. So what I am going to show, look at u prime in D that do not belong to some Sj, which basically does not belong on that tree, right. Now let's put back that edge and let's see what happens. Okay. Now this is my Tj. Now this is the edge u prime which we added. Okay. Now what happens? So then look at this path. Okay. Look at this path. If I show to you that on this path all the edges belongs to, if I show to you that all, look at this, if I add u prime in Tj, and what was this? It was not Tj, no? Yeah, Tj. If I show that all these edges belongs to D, then are we good? If I show to you that either this edge belongs here, or look at the path in Tj between u and u prime. If I show to you all the edges on this path also belongs to D, then they belong to Sj, and hence they belong, they are forming a path. Okay. But how do we show this? Okay. How do we show this? How do we show this?
We haven't used the fact that these and setup.
No, yeah. So look at why u prime is in D, because there is exchange chain starting at this, right? So there is exchange chain E0 En, where E0 is u prime. Okay, that's fine. Now look at any edge here, any edge on this. What about this? This is also exchange chain starting at any edge f on this path. Why? Because every other property is anyway satisfied, right? Now for f, right, what? So last guy does not belong to, last guy does not belong to, because last guy does not, it is last guy does not belong on any of this spanning tree by definition, right? And the first guy belongs here, and I could, like, now what is the property? That for every one there is someone which, so now I have done this, which implies that all of these guys can start a chain, and if they can start a chain, it means they all belong to D. If they all belong to D, then they all belong to Sj. It means between U and U prime, I have found a path, right? So that's it. I told you, right? Look, I'm just giving you sense of the proof. I don't expect you to, like, but how people go about it. What I wanted you to just take away is the statements. Okay, but we are doing course, so we should learn how to prove things. Okay. Okay. So this is done. Okay. Now if you go and read the proof in the textbook, it will have a bit more clarity what they are trying to say. Okay. So what happened? So we started with a spanning tree, set of families of spanning tree that maximizes something. Then we look at all the objects, which is this. We have done this. Okay. And so on and so forth. And we first told you, so now I told you that how are we going to get this? Look at this set of T edges. Okay. So I have still not proved this lemma. We'll come back to that lemma. Okay. But now I also want to prove that the last fact. Okay, so what we have to show, what was that? That if we contract these parts, then we can cover all the edges that are going across by small number of trees. Okay. I think. Okay. Okay. Is that obvious? So now notice each of these U1 to UL okay. So we have the only edges which are not, which we should cover are essentially those which are not on the spanning trees, or rather, okay, let me say what I am saying. Okay, so this is U1 to UL. Now you contract this guy because they all have spanning trees. You have contracted. Okay. Now, if I contract each, fix one tree T1, okay, and you contract this, right? So that is going to give you some T1 prime of, look at the G slash contraction of each of these guys, right? Now, look at the spanning tree that you get from here, like for the cross, that is T1 prime, that is T2 prime, and that is Tk prime. Okay. My claim is these guys cover all the edges of this. Why? Let's think of this way.
So when you are contracting, all the edges of D are the connected components of D are gone.
Connected components of?
D. This forms this EY. So contracting them, like,
No, no.
collapses all edges.
Look, what we have to show here. Look, when I contract these guys, okay, but look, D also had I'm a bit confused here. Let's see. It is very simple one-liner. At least this is simple one-liner here. So I look at G contracted B. Okay, I get this T1 prime, T2 prime, Tk prime. The claim is this covers all the crossing edges. Okay, claim is this covers all the crossing edges. Why? This is not clear to me. Right. Assume we are done. It's funky. Okay, look. So what we have been able to achieve by doing this is very simple, very funky. Look at D. How we constructed HV comma D. D contained all the edges from outside, right? D contained all the edges from outside. Now look at the connected components. Right? Look at the connected components, right? Where are the edges that is not in the spanning tree? Where are those edges that are not in the spanning tree? After I have contracted, do they exist?
They are all crossing.
They are not crossing edges, they are inside edges.
But EG minus AD.
What is the definition of D? Is this plus EG minus E pi. All the non-tree edges I use to form my partition. Right? So there are no non-tree edges anywhere left. Every non-tree edge is in one of them inside. Okay? This is why it's a clever proof. See, it's what, look, I do know EG minus E pi. Okay? Non-trivial objects for one purpose. What was the non-trivial purpose? To support spanning trees. And these edges, but to the covering. Like if I start, so what is my, look, what is, it's so beautiful. So you have K spanning tree which maximizes, right? You have made a partition in a way that all the edges which are not in the supporting trees, they become part of some partition, completely part of the partition, right? Because look at an edge here, right? Look at an edge here. By definition, if there is an edge here, they belong to the same connected component, right? If they belong to the same connected component, then they are either in U1 or completely inside U2 or completely inside UL. They are not crossing edges. So every edge which was not present on the spanning trees, okay, I have made them non-crossing. So every crossing edge which is present with respect to this partitions belong to spanning trees, right? So if I contract them, I have covered all the crossing edges with the spanning trees. Okay, this is what I told you. It was easy argument. Look, it's a clever argument. So everything which happened for this is a here. Okay, so I started. So the definition of D is very, very fundamental. Okay, so what do we started with D, and we comprehended this with EG minus E pi, like because you had a problem. So I said, look at. So this is how. So imagine. So what I'm trying to tell. I started with a spanning tree. My objective is the following: that I want to partition my vertex set in a way that all the edges which are crossing belongs on these trees. Okay, so every edge which does not belong somehow should become a non-crossing edges with respect to the partition I'm planning to define. So to do that, what I did, so to do that, I started with a graph which connected this, and my pieces were basically the connected components of those, right? So this was to avoid them as a part of the partition, right? So these edges were added to this edge just so that they are not part of the crossing edges, okay? And these edges were added so that you have enough of them to support K disjoint spanning trees, okay? So this is how it was. Two things were defined. Okay. Once I have defined this, the proof is very clear, no? Right? By definition, if I contract them, these are spanning trees. So that part is absolutely taken care of. So that is trivial part. What is a non-trivial part with respect to this partition? Because this partition is made that no edge which is not on this spanning tree is a crossing edge by definition. Okay, this is how I constructed my partition. So that part of my theorem is taken care of, right? Okay. Now the harder part was that how do I ensure that each of them do support enough spanning trees? Okay. So for that I still need this lemma that if blah blah has an exchange chain, then this. This proof is very simple, not very hard. We will come back and prove this. Okay. But how did we? So once we did this, we said, okay, somehow we assumed disjointness, somehow we used proved connectedness, and we were done. So how did we say? So in some sense, what it tells you that if you look at edge maximal this spanning trees, then what is the property is that with respect to this, if you look at this, you are getting some edge disjoint spanning trees, right? And of course they are connected. So it's a modulo this lemma, we at least understand the contour of the proof. Okay, and this is also some 5 line or 6 line, but they are very dense 5-6 lines. Okay, and if you do not understand the feeling of this definition, no, which takes some time to get used to this definition, it's like verifying proof is also a bit, I would say, cumbersome. But remember the statement. That is what will help you, right? So if you want to partition your graph into dense pieces so that there are not too many edges flying across, then remember, right? I mean, I don't know how to do an algorithm, but that is a very different question. But existence of such kind of partition is also very, very useful object. Okay, so
doesn't this like assume that there are k spanning trees in zero? Like you say pi equals even to k.
no, even if you have one edge, right? So what are you saying? I didn't get your point.
So like if G, let's say it doesn't have k spanning trees, there is no pi, right?
Yeah, but then we probably will take trivial, right? So look, or rather let's look at this way. If you could probably cover all the edges of your spanning trees, all the edges of your spanning tree with k spanning trees, suppose you could cover them, that's a right answer. Then what will happen? If you pick up single vertex each as your partition, that also will help, no? Right? So in that case, you are not going to get such non-trivial partition, you are going to get trivial partition. So if you are very highly connected, you are going to get a partition which is like V. If you are highly sparse, very sparse, like done as you say, for example, if I had a spanning tree, there is no way I can come up with a non-trivial part where I can support 2 spanning trees, right? So what will you come up with? You will come up with a singleton partition. So this is what is happening when you say, if I don't have enough, then probably that don't have enough will be seen into your partition by coming up with a partition which is like singletons everywhere, because you can do things. So look, if it is yes of any of these two, right? Yes with respect to covering, trivial partition works. Yes with respect to packing, a trivial partition containing V. It's interesting when neither of these happens. Then you will start to get a non-trivial V, non-trivial decompositions. Okay, so next, so I will leave this, I will let you absorb this definition, and we'll try to come back next time and try to prove this and go over the proof once again to see the very subtle points of this proof. Okay.